May I have your attention then? I would like still to continue discussion on chapter 2. I would like still to say a few words about vectors. If you read the chapter, probably you saw that every vector can be written as we say it as a linear combination of vectors I, J, and K. In general, actually, this is the case for any type of vector space, that we can find a smallest set of vectors, and because I made it a little bit more general, so instead of writing I, J, and K, I write E1, E2, and so on. So these are some vectors, and we will call these vectors the base vectors, and these vectors have such a property that any vector can be written as the sum of products of those vectors from the set and some numbers. Yeah, like in the book, E1 is I, E2 is J, E3 is K. Vectors, these vectors I, J, and K, or in general these vectors over here, are referred to as the base of the of that space. Now, I want you actually to learn a certain terminology, and I for some reason you will have a problem with this too. If I write it if I write a vector or represent a vector as the sum of those products, the numbers which we have over here are called scalar components of the vector. Why don't we repeat it? So this is scalar component of a vector. Okay. Now, the number multiplied by that base vector is called vector component of a vector. Say it. And I bet that tomorrow on the quiz, some of you will say that vectors I, J, and K are the vector components of the vector. Consult with your neighbor what's the difference between the vector component of a vector and that error which you are going to make tomorrow. Can you see the difference? Yeah, vectors I, J, and K are not vector components of a vector. We have to multiply each of those, I, J, and K, by what in order to get vector components? By what? Not by, we cannot multiply by a direction. There is no such operation. We have to multiply those base vectors by, actually we know only one multiplication of a vector so far. Today we will learn another one. By a number. The only thing by which we know so far how to multiply a vector is by a number. Right. So we have to multiply base vectors by certain numbers in order to get vector components of a vector. What do we call those numbers? Scalar components of the vector. Correct. Right. Good. Now, depending on this, how many base vectors we need to represent every vector in the space, we assign dimensionality of the vector space. So if we have only two, if we need only two base vectors, then we say that this space is two-dimensional. Think about arrows on the whiteboard. I'm not sure if I will be able to draw them. No, I won't. So think about arrows on a plane. How many base vectors would you need to represent every arrow on the plane in terms of linear combination of those base vectors? Two, correct. If you use two vectors, it means that the whiteboard is two-dimensional. Now, in the room over here, we will need three. And actually, consistently with the book, what are the names of? Let's name those three vectors the same way as the book does. So it will be vectors I, j, and k. We take those three vectors, therefore this space is three-dimensional. Let's take a look at an example, and actually one more thing. In a way, you could even think that I kind of deviate from the book because writing down every vector as a linear combination of vectors I, j, and k, well, it's a lengthy expression and has ambiguity. Not ambiguity. Yes, it does. Not ambiguity, but redundancy, and it is kind of inconsistent with your calculus book. So in a calculus book, or even I don't know which one, but computer scientists also don't write linear combinations. They rather write arrays. All right. So if I take, let's say that I have an arrow, A, and I write this as a linear combination of three arrows which constitute the base. If I take those three arrows to be mutually perpendicular and each of them of unit length, I will form something which is referred to as a Cartesian system. And to each of those arrows, I will assign an array of scalar components and represent vector A as a triad of scalar components. So I can recognize that if I have an arrow and this and these axes, I can now use these directions, x, y, and z directions, to form such a block that the arrow, considered arrow, is the diagonal of that block. Well, if it is a diagonal of the block, I can recognize that actually it is a sum of those three vectors. And each of those vectors now is a product of a vector of unit length in this direction and a certain number. Now, what would be the number actually? Let's say that I think about vector AX. What number should by what number I should multiply vector I in order to get vector AX? Note that vector AX actually, if we use that previous slide, vector AX is a certain number multiplied by I, which means that that number AX is going to be the what? Scalar component of vector A, and product of AX and vector I will be the what? The vector component of vector A, correct. So actually this arrow, and this arrow are the vector components of vector A. Now the numbers by which I have to multiply I, j, and k are the scalar components of this vector. All right, so let's say that this arrow has length 3 units. By what number I would have to multiply vector I, which will have length of 1 unit, in order to get vector AX? By 3, correct. Well, if it were 5, length were 5, by what number I would have to multiply vector I? By number 5. So every time I have to multiply by the length of this arrow. And along y-axis is the same thing. If this length is 3 and this one is 1, so I have to multiply vector j by number 3 to get this vector. All right, so, and these numbers now are the scalar components? Well, so vector A can be written now as a linear combination of vectors I, j, and k, with ax, ay, and az being certain numbers. Well, this is a lengthy notation, and actually ij and k would repeat itself everywhere. So rather than doing this, I prefer to use a triad of numbers, or an array which contains scalar components of vector A. So this array is an array of what? Not vector components of vector A. Scalar components of vector A, correct. For some reason, I don't know, people will put vectors I, j, and k in that too. I bet that you will, which is as complicated as this expression. All right. Now I want to introduce second multiplication, which is very important actually in physics. It is called the scalar product of vectors. So far we know what? What multiplications do we know? How many multiplications do we know? Assuming that you learned only those multiplications which you learned in grammar school and here in this classroom. How many? Numbers. We know how to multiply numbers and how to multiply a number by a vector. Today we are going to learn how to multiply a vector by a vector, and it happens that in science we have two multiplications of vectors, two different multiplications of vectors, and we give them different names. So today we are going to learn how to multiply two vectors using scalar product, and in the future we will learn how to multiply two vectors using vector product. Sometimes scalar product is referred to as a dot product, and I will accept that. Vector product is often also referred as the cross product because of the symbols for multiplication. Scalar product is defined in such a way that it has to satisfy these four conditions. It has to be commutative. I use open circle now for multiplication, for this multiplication, for scalar product. So for regular product we use, for product of numbers we use a dot. For product of a vector and a number we use a bullet, and a circle for scalar product. Now, it is kind of redundant notation because I could, and the book does that for all three uses the same dot. There is no ambiguity in it because how to distinguish between product of numbers, product of a vector and a number, and scalar product if I use the same symbol for multiplication, a dot. How to distinguish between these three multiplications? The elements which you multiply, the factors. If you have two numbers, then it's product of two numbers. If you have a vector and a number, it's that bullet. If you have two vectors and a dot between them, it means that it's a scalar product. Now, scalar product is called scalar not because we multiply scalars, because this will be also a common error. I bet that in a week you will say that 2 times 3 is scalar product. It's not. It's what product? Vector. No, if numbers. This is product of numbers. 2 times 3 is product of numbers. All right. So it means the first condition is commutative. It means that result does not depend on the order in which we multiply. Oh, I forgot to say one thing. Scalar, I haven't finished it. Scalar product is called scalar because the result is a number. If we multiply two vectors using scalar product, we should get a number. All right, and that number should not depend on this in which order we multiply. It is associative. Well, actually, here we have again mixed associative condition, because if we multiply one of the vectors by a number, it doesn't matter if we first multiply the vector by a number and then multiply the result with the second vector, or, and actually here is an error. There is an error over here. I'm sorry. Find the error. Yes?
The open circle is inside the parentheses on one, but the bullet point is inside the parentheses on the other, so it's different kinds of multiplication.
Wait, so you say that this, which one is wrong? This one?
Yeah.
Correct. This one is wrong. You see that? Because if I multiply a vector by a vector using scalar product, I will get a number. So here I have product of two numbers. Make sure that in your notes you have it right.
Should be a dot, right?
Should be a regular dot, correct. It should be a product of two numbers. How about here? Is this here correct? Yes. How about that one? It is also correct, right? Because if we multiply a vector by a number, we'll get a vector. All right. The third condition is that a scalar product is distributive. It's also kind of mixed distribution. Because if I calculate scalar product with the sum of vectors, I can multiply each of the vectors separately. And, oh, did I make an error here with this plus? No, that one is correct, because if I multiply the first term with the with this vector using scalar product, I will get a number. Multiplying the second vector by a vector using scalar product gives me another number, which means that I'm adding here two numbers. Now the last condition is that if I calculate scalar square, I should not get a negative result. Multiplying vector by itself should give me 0 or a positive number. And we can get 0 only under one condition. If we multiply vector 0 by itself, we get a 0 number. Note, by the way, that the zeros are different. This 0 is different than this 0. Can you see it? And why it is different than 0? What is this 0?
It's a number.
This 0 is a 0 number, correct. What is this 0? This is a 0 vector, correct. All right, let's now, I will now introduce the product for the two vector spaces which we are discussing so far. So for arrows and for arrays. So if I have two arrows, scalar product of two arrows is calculated by taking the lengths and the angle between the vectors. So scalar product of arrow A multiplied by arrow B is equal to length of arrow A times length of arrow B times cosine of the angle between them. Why don't we find scalar product of two vectors of unit length? So scalar product of vectors I and j, for example. What is the scalar product of vectors I and j? Oh, quickly calculate that. Why don't you answer it before I show the answer? This is how we should calculate it. Think about product of vectors I and j. How much did you? What's the answer?
Be I times j times cosine of a.
I is not a number. Over here, look, then when we calculate I is not the length of vector I. When we calculate scalar product, we don't use here vector A. We use its length. So if I think about vector J, I shouldn't use here J, but I should figure out what is the length of vector I. Well, how about if I just show it? If vector A and B have a length of 1, well, then I take 1, because this is length of arrow A. I multiply it by another 1, because it's the length of arrow B. They are perpendicular, which means that the angle between them is 90 degrees. Cosine of 90 degrees happens to be 0. So if I multiply 1 times 0, I'll get 0. Now, if we take arrays, we multiply them, scalar product is defined in such a way that we have to multiply first number by first number, second number by second number, third number by third number, and so on, and then add those products. So scalar product is calculated by adding products of corresponding arrays. Well, how about if we do an example? Why don't we find out scalar product of these two triads? Can somebody help me with that? How to do this?
Do the
1 times this 2, correct? So it is 2, right? Negative 1 times 3, so it's negative 3. And 2 times 0 is 0, so the answer is? I don't think so. Negative 1. Now we have to add those three products. Yeah, so it will be 1 times 2 plus minus 1 times 3 plus 2 times 0. If we add all of that, we will get minus 1. Note that in both cases, the result was a number, correct. You will have a problem with that too. I know that some of you will calculate scalar product and still will get a triad. In other words, a vector. Now, that Cartesian coordinate system was introduced in such a way that if I take triad of scalar components, I can easily find scalar product of the vectors which they represent. And here's the derivation. Why don't we actually try to comprehend it? So over here, I calculate scalar product of two arrows. Now I'm abandoning already this unambiguous notation. So I assume that at this point you already do not confuse product of numbers with the product of a vector and a number. So I will use the same symbol consistently with the book. Also, I will assume that right now you do not confuse additions. What additions? Additions of numbers and vectors, correct. All right. So here I represented vector A as a linear combination of base vectors. Just to make sure, what kind of addition do I have here? Faster. No! Vectors. This is addition of vectors over here. Where did I get it from? Why is it addition of vectors? Because we have I, J, and K, and they are multiplied by a number. Correct? Yes. So this is a number. This is a vector. This is multiplication of a vector and the number. The result is a vector. This is a vector, this is a vector, and this is a vector. So all three are vectors. We are adding vectors here. You have a question here or comment?
No, how come you're using that addition sign?
The what?
That addition sign?
Because I'm trying now to switch back to the book, right. So I hope that at this point you already are sufficiently familiar that I'm coming back to the book's notation. If you are still confused, you can put circles. There's no room for bullets, because over here you would have to put a bullet. I still keep a separate symbol for, if you look at the page, separate symbol for what? For multiplication of vectors. Which multiplication of vectors? But which, what do we call this multiplication? Scalar product. Yes, I keep different symbol for scalar product. All right, so I wrote here, I expressed here vector A as a linear combination of the base vectors. And how can I do it? What is the basis for it? Yeah, because base vectors are selected in such a way that every vector can be represented as a linear combination of the base vectors. So I could do it. I was able to do it. I'm also able to represent vector or express vector B as a linear combination of vectors of the unit of the base vectors. What addition do I have here? Fast. Vectors. Good. All right. Now, if you look at the properties of scalar product, one of them is that scalar product is distributive over addition of vectors. So using this one, using this property will result that every term from this sum has to be multiplied by every term from this sum. All right. So here I have the first term multiplied by the first term. Now, the length of this vector, which actually is the vector component of vector A in x direction. Can you recognize that this entire term is the vector component of vector A in direction I? This is vector component of vector A in direction J, and corresponding, this one is K. How about A1? A1 is what? Scalar component, right. All right, so length of this vector component is A1. So I put A1 here. Now length of this one is B1. So I put B1. And I take cosine of the angle between these two vectors. Well, the angle between these two vectors is the same vector, so angle is 0. So I put cosine 0. Now product of this one and this one, well, actually, rather than thinking about lengths, it's better even to look at the properties of fact that scalar product. I mean that the scalar product is associative. So rather than multiplying, I mean coming back to this one. If I look at this expression, this term and this term, over here I have to multiply first vector I by A1 and then multiply it by this expression. I can pull out A1 and say that this is A1 multiplied by a product of vector I and of this one. Now scalar product is commutative. I can change the order of these two vectors I and B1J and do the same thing with B. So I can pull out B. And then I will be left with scalar product of vector I and vector I, which will be 1 times cosine of 0 degrees. I can do now this with first term from here and second term from there. So I will pull out A1 and B2, and then I will have scalar product of vector I and J. So it will be 1 for length of vector I times 1 times cosine of 90. And I can continue like that. Now, repeat it. Why is it A1 and B2? It came by multiplying the first term from the first sum with the second term from the second sum. Now this term came from multiplying the first term from the first linear combination and third term from the second linear combination.
I got that part, but when you use the distributive, what was the point of pulling out the, like on that first expression on the second line, what was the point of pulling out the A1 and the B1? So you can just have I and J?
Well, no, I got, know that over here I already got rid of them. Instead of having I, J, and K, products of them, I recognize that they are cosines of either 0 or 90 degrees. So I don't I don't have I's and J's here anymore. Who is confused about that? Talk to each other. Have a conversation. How did I get these terms? Have a brainstorm now. What did you say?
Cosine of 0 is 1.
Cosine of 0 is 1.
Cosine of 90
is 0.
So
Right.
You just simplified it down here
Correct.
because all the rest of it just cancels
Correct.
out. Well, that's the angle. That's
Correct.
that angle I. Is cosine.
Correct, because
Oh,
vectors I, J, and K are mutually perpendicular.
okay.
Okay, why don't you come back? I think that I got here a very valid question about, because it is obvious that angle between a vector and the same vector is 0 degrees, but where that 90 degrees came from? Well, that 90 degrees comes from the fact that we are talking about Cartesian system, which means that we choose the base vectors to be mutually perpendicular. So vector I is perpendicular to vector J and vector K. Maybe I wasn't sufficiently clear about that. I thought that you got it from the book. Vector J is perpendicular also to I and K. And K is perpendicular to I and J. Those every pair is perpendicular. So wherever we have one base vector with a different base vector, we get 90 degrees. Whenever it is a base vector by itself, we get 0 degrees. All right. Now, cosine of 0 degrees happens to be 1, and cosine of 90 degrees happens to be 0. Correct. So, which means that a lot of those terms are zeros. This one is 0, and this one is 0. This one is 0, and this one is 0. This one is 0, and this one is 0. The only non-zero terms are these three. And on top of it, cosine is 1. So actually, from this term, I get that it's A1 times B1. Here I have A2 times B2. And here I have A3 times B3. Now, A1, A2, and A3 are what? What are they? Let's phrase it in English. We gave a name to that. To vectors, to numbers A1, A2, A3. Scalar components of vector A, correct. And B1, B2, B3 are scalar components of vector B, correct. So when I calculate scalar product of two arrows, I can just take scalar components of those arrows in a Cartesian coordinate system and use a scalar product which we define to arrays. Right? So I have to just take array of scalar components and multiply arrays of scalar components, and the result will be the same as multiplying the two arrows. I want you actually to be flexible with this, because in one situation it will be more easier to use directly the definition of multiplication of arrows, and in the other situations it will be easier to use the arrays. Yeah, so If I know scalar components of the two vectors, what formula I would use to calculate scalar product? The arrays, that one. I will multiply first component by first component, add product of second component by second component, and add product of third component multiplied by third component. Now, if I knew the lengths of the two arrows and the angle between them, how would I calculate scalar product? Which means, how would I do that? Say what I will multiply by what? Length times cosine of the angle between them. Right. All right. Now, if we have a physical vector quantity, to physical vector quantity, we assign an arrow, and if we assign an arrow, we assign also an array. Scalar product between, let's say, force and displacement will be calculated through the scalar product of arrows or arrays, which are assigned to those two physical quantities. And because of that, we will never imagine really physical quantity. We will always imagine either arrow assigned to that physical quantity or a triad of numbers assigned to that physical quantity. You are unable to imagine force. Whenever you think about a force, because some of you already have some kind of intuitive picture of it, and when you think about it, you think about an arrow heading from an object. Try to think in terms of what really it is. It's impossible. All right. Now I want to formalize a concept which concerns all vectors, and it is referred to as magnitude. Before we introduce concept of scalar product, concept of magnitude does not exist. Magnitude is defined as square of scalar square of a vector. So magnitude of, in order to find out magnitude of vector A, I have to multiply vector A by vector A using scalar product and take square root of that. If I take square root of this scalar square, is it true that I will get a vector?
No.
No. Why not? Because it's a number, correct. Look at that. If we calculate scalar product of vector A and A, we will get a number. If we take square root of a number, we won't go back to vector. We will get a number. Not only that, we will get a non-negative number. Now that something like this happens also with in numbers as well. If I square number and take square root of it, I don't have to take the number. I will not have to get the number. I have to get a number, but not the same one. What number am I going to get? Show me that it is. Show me an example that it's not the same number. Negative number. Square root of -1 square happens to be 1, not -1. All right. So let's now think about magnitude of an arrow. Well, if I want to find magnitude of an arrow, I have to, and actually consistently with the book, I mean, although probably on the screen it is not as clear as it is supposed to be, but the book uses regular letter to represent a magnitude of a vector. So in the book that letter is not bold, and over here it isn't bold either, although I must say that can you see that this letter is different than this one? Now when you write, it is difficult to write bold letters. So rather than writing bold letters, put arrows above all vectors. And if you miss an arrow, I will automatically assume that you are referring to magnitude of the vector. So do not confuse those things. Well, how about if we now make, you will shout, what letter we should use, regular or bold, and I will give a name of something. Yes. So, for example, if I want to use symbol for a vector, I use what letter? Shout. Bold. Correct. If I use symbol for magnitude of a vector, regular. Correct. If I use a symbol, what letter do I use for a scalar component of a vector? Consult. Quickly consult. Scalar component of a vector should be a bold symbol. We should use bold symbol or regular symbol. Who votes for regular? Who votes for bold? Regular. Scalar component of a vector is a number. Therefore, we should use a regular letter. How about vector component of a vector? Who believes that we should use bold symbol? Who thinks that we should use regular symbol? Those of you who thought that we should use bold symbol, you were right. Vector component of a vector is still a vector. All right. Recall that it is number, scalar component multiplied by the unit vector. All right. In many books, and actually if you have an expression, a vector expression, we will have to use these vertical lines to indicate magnitude of a vector. Well, by definition of magnitude of a vector, I have to square that vector and take square root of it. Now, for an arrow, I have to square, well, so I have to take a length of vector A, multiply by length of vector A, and multiply by cosine of 0 degrees. Cosine of 0 degrees happens to be 1. Length happens to be a positive number. So if I square length and take square root, I will get length of an arrow. What's the conclusion? What did I just get? That the magnitude of an arrow is equal to its length. Yes, so make sure then when you will be making, because magnitude will be even more useful than the length, because we will use arrows to represent various quantities. So it is going to, for example, represent a force. Well, magnitude of an arrow should be such that it is consistent with the magnitude of the force. Therefore, you will have to choose appropriate length of the arrow to represent the force. Do you see that? All right, so how about if we stop at this point and see you tomorrow.